In this video, we're going to continue analyzing intermodulation terms in our amplifier model. The remaining term of interest is the third order term under the effects of a two-tone test. And if we expand that term into a polynomial, we'll find that it contains third order harmonic distortion terms for each tone, and then two new third order intermodulation products. Those intermodulation products expand into this expression, which you can prove to yourself at home using our previous expression for cosine squared and the angle addition formula. I encourage you to pause the video and do this short derivation for yourself. I've included the whole output expression for a two-tone test on this slide. The new developments, which I've just underlined, are that third order intermodulation produces more gain compression on each input tone, and a handful of new tones at 2 omega 1 plus or minus omega 2 and 2 omega 2 plus or minus omega 1. The gain compression is no different than harmonic distortion in the sum terms, the 2 omega 1 plus omega 2 and 2 omega 1 plus omega 2, 2 omega 2 plus omega 1, are close to the third harmonics, which makes them easy enough to filter out. However, the difference terms, the components at 2 omega 1 minus omega 2 and 2 omega 2 minus omega 1, fall very close to the fundamental frequencies, which makes them difficult to filter from your signal. These difference terms are often said to be in-band, referring to the range of frequencies your input signal occupies. We can define a metric for third order intermodulation by comparing the amplitude of the in-band intermodulation products with one fundamental tone. That results in a metric that is 3 times larger than HD3. The frequencies from the full amplifier output expression above appear here. You can see that there's a pattern of intermodulation making tones near harmonic distortion, such that you're left with these little pyramids in your spectrum. These pyramids extend further if you apply input powers sufficiently high to create fourth and fifth order harmonic distortion. However, again, the most problematic parts of this spectrum are the in-band terms at 2 omega 1 minus omega 2 and 2 omega 2 minus omega 1. So in summary, third order intermodulation products at 2 omega 1 plus or minus omega 2 and 2 omega 2 plus or minus omega 1 and omega 2 are the result of this nonlinear process. Also, third order intermodulation is described by the IM3 product, which is shown here. And finally, third order intermodulation creates a rich spectrum that consists of these little pyramids around each harmonic of your test tones, and it's worth kind of looking at this plot and making sure that you have a good copy of it in your head.